In this video, I want to walk through an example of a hypothesis test using a p-value method. All right, using the p-value method in step number 4, as you can see here, I've got 6 steps outlined as far as how to go through hypothesis testing. But step 4 is where we determine the p-value, which is different from step 4 in the critical value method. All right. Well, first off, what you need to know is we need to state the null and the alternative hypotheses, and I really recommend that you decide which one of those is the claim. And that's important because when we get to step 6, when we get to the final step and we state a conclusion of the hypothesis test, we're going to phrase that conclusion in terms of the claim. Okay, so first off, let's go state the null and the alternative hypotheses based on this problem down here that you see at the bottom of your screen. We have batteries for a toy car. They're designed to last 30 hours on average. We know what the population standard deviation is. It's 2.95 hours, so we know what sigma is. But a lot of customers have been complaining that the batteries did not last 30 hours. They were lasting less than 30 hours. So that's also key there. The less than is important. We're going to need that for the alternative hypothesis. So you decide to randomly sample 38 of the manufacturer's batteries. That's little n, that's your sample size, 38. And the mean of those 38, the x bar, the sample mean, had a mean life of 29.3 hours. So we're going to ask this question: is there sufficient evidence at the 5% level of significance? Right, that's important. We're going to need that when we compare our p-value in just a moment. Is there enough evidence to support the claim that the mean battery life is less than 30 hours? All right, so here goes. Let's first define the hypotheses. And as far as the definition of the hypotheses is concerned, we're going to base this off of the population mean. Now that's supposed to be a mu, but I'll just use a lowercase u for this one. Right? So the claim, or rather the battery life is supposed to last 30 hours. So the null hypothesis always has an equal sign in it, and so I'm going to set this as mu is equal to 30 hours. There we go. Now the alternative hypothesis, this is where a lot of the customers were complaining because they felt that the population mean was actually less than 30 hours. So there's our alternative hypothesis. Now before I go any further, I want to do something that's really important. I am going to draw an arrow here, and that's going to signify that this thing here, the alternative hypothesis in this case, is our claim. So I'm just going to put here claim. A little chicken scratch there. Okay, so this is our claim. This is really important. It's important because when we get to step 6, here I'll even highlight this. When we get to step 6, we're going to decide what we're going to say about the claim. We're either going to support it or we're not going to support it. So it's important to know which one here is our claim. And in this case, the alternative hypothesis is the claim. The claim is from those customers saying it's less than 30 hours. It's not 30 hours or more. Okay, so step 2 rather, is now our level of significance. Well, that's based on what they told us in this problem here. Our level of significance is going to be 0.05, right? We were basing it off of a 5% level of significance. Sometimes that level of significance is 10%, sometimes it's 1%, sometimes it's not even given, and you have to determine what the level of significance is. Typically 0.05 or 5% is probably the most popular of those of any level of significance of those three. Okay, so we have a level of significance. That's important. We're going to need that in just a bit as well. Let's move down now to figure out what our test statistic is going to be. All right, I've got a formula here for test statistic. It's take your sample mean minus the population mean, which in this case mu sub x bar is 30 hours. And we're going to divide that by standard error, or standard error of the mean, sometimes people call it. And standard error in this case is sigma, the population standard deviation, divided by the square root of n, or divided by the square root of our sample size. Let's see, I've got my calculator here. We can just crunch all these numbers. Okay, so I've got 29.3, that is our sample mean, minus 30, that was our population mean, that was our mu based off of the null hypothesis. All right, I've got that in parentheses because I want that to be done, that difference to be done in the numerator. Divided by, open up another set of parentheses because we have two things going on in the denominator. I've got sigma, which is our population standard deviation, 2.95, divided by the square root of little n, which in our case is, we had a sample size of 38. So I'm going to do all this here on my calculator, and it gives me a z-value. A test statistic is a z-value. It's a standardized number of negative 1.46. All right, so I'm going to type that in over here. Negative 1.46. Now, here's where the p-value part of this comes in. What is the area in the tail? Now, this is important. What's the area in the left tail? And I'm going to show you why it's left tail in just a second. If the z-value is negative 1.46 based off of our test statistic. All right, so what I'm going to do then is let's look at this picture over here that I started to draw. And this is not a perfect picture by any means, but I know that negative 1.46 is somewhere to the left of 0, to the left of a population, or rather a population mean of 0. Okay, that has to be in the middle. So I know that negative 1.46, z number, is somewhere to the left of it. And I'm going to shade to the left of this negative 1.46. And the reason I'm shading to the left and not to the right is because of this right here. I hope you can see. In fact, I'll circle it for you in the alternative hypothesis. Right? The claim was that we were looking for that the population mean was less than 30 hours. All these complaints came in saying these batteries don't last that long. They're less than 30 hours. So because this is a less than symbol, that means I need to shade to the left. This is important, okay? If this was a greater than symbol, then I would have shaded to the right. Hope you can read that. That says left, okay? So I'm shading to the left of negative 1.46. My question is, what is this area over here? What is this area? And it turns out that this area is the p-value. Yeah, the area in the tail of the test statistic is the p-value. That's important. Okay, so we can use our calculator to do this, or we can look this up on a normal distribution table. Let's see, to do this with our calculator, I guess I can show you this here. We could do second distribution. Normal CDF is the function that you want. And so what you need to do is you need to feed it some really, really small z-value that's way out here to the left, as far left as you can go. This is what we call the lower bound. And so some small number way out here is like negative a million or something. You don't have to even go that far. Just a negative 10 is probably as far as you need to go. And then you need to, after you do that, put in comma. Now give it the upper bound. In this case, what's the farthest right that the shading will show you here? The farthest right of the shading is a negative 1.46. This is our upper bound. So I'll punch in a negative 1.46. Close off that parentheses. That's all we need to do. And press enter. And you can see that our z-value, our probability, our area, is 0.0721. We'll go out to 4 decimal places. So 0.721. All right, that is our p-value. This is really, really important here. Okay, so 0.0721 is our p-value. Okay, so now what I'm going to do is I'm going to compare two things. I'm going to compare our p-value. Let's see if I can draw this up here. Our p-value of 0.0721. 0.0721. That's this area sitting right here, 0.0721, to the left of negative 1.46, the z-score, or test statistic. All right, I'm going to compare that to our level of significance that we were given in step 2, which is 0.05. And I hope you see that obviously 0.0721 is greater than 0.05. Right? It's greater than 5%. So if and this is how the phrase goes, if the p-value is high, then the null must fly. All right, if the p-value is high, the null must fly. What does that mean? That means when we get to step 5 now, we can say, okay, our conclusion about the null hypothesis is that we are going to fail to reject the null hypothesis. We're going to fail to reject the null hypothesis. In essence, I'm almost doing this in quotes here. I'm basically saying we're going to accept the null hypothesis. We're not really accepting it. We don't say that. We state it as we fail to reject it. We're not going to reject it. Another way to do this is, and I often do this in class, is I say, all right, let's go over here to our null and alternative hypotheses for a moment. If I fail to reject the null, I like to sometimes just draw an arrow pointing up on the null. That's supposed to be an up arrow. It's really hard to draw. Which means, in essence, I am pointing an arrow down on the alternative. It's like a thumbs up on the null and a thumbs down on the alternative. What I just did, I hope you see, if I thumbs down, if I point an arrow down on the alternative hypothesis, then I am rejecting this claim. I'm basically saying this isn't true. I'm still agreeing with the null hypothesis here. So I am rejecting the claim. And that's where step 6 comes into play. This is our final and last step. Now that we know that we're going to accept the null, so to speak, and reject the claim, then my conclusion statement is going to be, there is not sufficient evidence to support the claim. And I got to be a little bit more specific. I have to also state at the 5% level of significance. Right? That's important because what if the level of significance wasn't 5%? What if it was 10%? What if this number right up here wasn't 5%, but what if it was 10% level of significance? You would see that our p-value of 0.721 is actually smaller than 10%, and in that case we would reject the null hypothesis. So watch out for that. That's really important. We have to make sure that our p-value is compared to the proper level of significance, our alpha, and so when I make that claim down here, I have to state that that I am either supporting the claim or I'm not supporting the claim. There's enough evidence to support it or not to support it, and I have to be specific and identify at what level of significance. So in this case, there is not sufficient evidence to support the claim at the 5% level of significance. That's how p-value hypothesis testing works. You're going to compare the p-value, which is the area of the tail, or tails if it was two-tailed. So the area of the tail based off of the test statistic. Really, really important. We're going to compare that to alpha, and if it's high, the null must fly. We get to keep it, thumbs up on the null. If it's low, then the null must go. We don't get to keep it. In that case, we would be supporting the claim. So I hope that helps, hope that makes sense.